Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing to look at carboxylic acids. Specifically, we're going to examine reactions of carboxylic acids. Now, as mentioned previously, a major property of carboxylic acids is the ability to delocalize a negative charge over two atoms after it's lost a proton. This is due to the side-to-side overlap of the two p orbitals in the sp² atoms. Understanding the factors that affect acidity will be crucial to understanding the behavior and chemical reactivity of carboxylic acids. Now, at the bottom of this section, I have included a listing of relative rankings of pKa's of various functional groups. Alkanes have pKa's around 45 to 50. Alkynes, approximately 25. Alcohols, 15 to 19. Phenols, around 10. Carboxylic acids are weakly acidic, having pKa's around 5, which are less than HCl and HNO3, which have pKa's less than 1. We're going to review now factors that are important with regards to chemical structure that affect acidity. We're going to begin by looking of the effect of structure upon acidity, specifically that of electronegativity. One very important factor in establishing trends in acidity is understanding the role electronegativity plays in acidity. The higher the electronegativity of an atom, the more likely it can bear the negative charge after the proton is lost. If I compare, say, methane reacting with H2O, going to CH3 minus plus H3O plus, the ability of carbon to bear that negative charge determines the ease with which the loss of H plus occurs. If I now take neutral NH3, react it with H2O, and compare the same reaction, producing NH2 minus and H3O plus. NH2 minus has a negative charge bound to nitrogen, which is more electronegative than carbon. That means the negative charge is more stabilized, or the loss of H plus is more facilitated. The higher of electronegativity of nitrogen makes NH3 a stronger acid than CH4. Atomic size is also crucial to understanding trends in acidity. If I compare, for example, hydrofluoric acid when it reacts with water, producing F minus and H3O plus, to hydroiodic acid, HI plus H2O, giving us I minus plus H3O plus. I is much larger than fluorine. Because of this, the large size difference between the iodine and the hydrogen results in poor orbital overlap, so the bond breaks more easily. It is a weaker bond. In this case, the HI bond breaks more easily, releasing H plus more easily, making HI the stronger acid. This is due to poorer orbital overlap. We have also learned about trends in hybridization. In terms of hybridization orbital size, sp cubed orbitals are larger than sp squared orbitals. See, the p orbital is more diffuse, and as a result, more p character means a larger orbital size. sp being the smallest. That means sp cubed has its orbital or its electrons further away from the nucleus. That is parallel to being less electronegative. More electronegative atoms hold electrons closer to the nucleus. Effectively, because it's smaller, the sp orbital is the most electronegative. The net result of this is if I compare, say, CH3, CH3, ethane reacting with water to produce CH3, CH2 minus, and H3O plus. Say I compare that to HC ethine reacting with water. Because the hydrogen-carbon bond in ethine is the overlap of a 1s with an sp cubed. And when the H plus leaves, the negative charge is in a 1s with an sp. And when the H leaves in ethine, the lone pair of electrons here is in an sp orbital. That lone pair of electrons is closer to the nucleus. It's like it's more electronegative. And because of that, it's more stabilized. Hence, due to hybridization effects, alkynes are more acidic than alkanes. We can even see acidity trends due to inductive effects. Inductive effects. For example, if I compare formic acid reacting with water, producing H3O plus and the formate anion, and I compare that to what occurs if you put a more electron donating group in. Methyl, through sigma donation, pushes electrons into the carboxylic acid. And compare that to when you have an electronegative group that's withdrawing electrons through its sigma bond. If you make a list of pKa values for these, the pKa of formic acid is about 3.75. When you put a methyl group on, pushing electrons in, we get a pKa of 4.75. A larger number means weaker acid. And with the electronegative chlorine withdrawing electrons from the carboxylate, the pKa drops, making it a stronger acid. See, the loss of a proton results in the formation of the CO2 minus group. Electron donation from the methyl pushing electrons in reduces the stability of the CO2 minus, whereas the electronegative chlorine stabilizes the formation of the CO2 minus, with the chlorine withdrawing electron density and helping stabilize the buildup of negative charge. Such inductive effects vary with regards to the degree of inductive electron donation or the electron withdrawing properties of the group in question. Groups can be ranked in order of increasing electron withdrawing ability. So I could make a general trend. For example, methyl groups are one of the least electron withdrawing. They're actually electron donating. So in terms of what electron withdrawing ability, methyl is less than hydrogen, who's less than an alkene, who's less than an aromatic ring, C6H5, which is less than HO, which is less than methoxide, which is less than I, which is less than Br, who of course is less than Cl. Now in terms of carboxylic acids, if I take CH3, CH2, CO2H, and I compare it to CH3, CO2H, and I compare that to when you put an alkene on, when you put the aromatic ring on, and we'll continue with this. We can see these electron withdrawing trends parallel acidity trends according to pKa values. So pKa of propanoic acid is 4.87, acetic acid is 4.75. Put an alkene on, you drop to pKa of 4.35. The aromatic ring drops to 4.31. And the pKa value for the hydroxy off the acetic acid, 3.87. And once you put on the electronegative chlorine group, you get a pKa of 2.81. Now, the inductive effects will increase as you add more and more chlorines. If I compare this to, say, Cl2, CH, CO2H, and Cl3, CCO2H. The pKa begins to drop rapidly, going to 1.29 and 0.7 for the trichloroacetic. So the electronegativity effect, or stabilization of the resultant anion, is additive as you add more chlorines on. The effect does fall off rapidly, however, if you move the chlorines further away from the carboxylic acid. What do I mean? Well, suppose I rub this off. Suppose I put chlorine on, and I start with a fairly long carbon chain with no chlorines on, CH3, CH2, CH2, a butanoic acid. Butanoic acid has pKa around 4.8. If the chlorine is very far away, so you have like a CH2, Cl, and you have two CH2s, there's only a tiny effect because the electronegative chlorine is so far away, can't stabilize the anion that would form very much. There's only a tiny effect on pKa. As you move the chlorine closer, the effect increases. pKa now is 4.0. And of course, when it is right next door, we've already seen this, the pKa drops down to almost 2.8, about 2.9. So there is a sharp drop-off of the electronegativity effect as you move the electronegative groups further away. So electronegative groups off the carboxylic acid help stabilize the anion, so increase acidity. Electron donating groups reduce the acidity effect. As per usual, I do not expect you to remember these pKa values. However, you should be able to give general trends. The next effect we want, of course, look at is an important one for carboxylic acids, and that is resonance effects on acidity. Resonance effects. In the case of a simple alcohol, loss of a proton is not very favorable. Even though you have an electronegative oxygen, the problem is that the resultant anion localizes the negative charge on that oxygen. There is no resonance stabilization, and all you have is the electronegative oxygen. And while that does stabilize somewhat, it's not enough to turn an alcohol into an acid. Phenols, on the other hand, can react with water. And if they deprotonate, actually, let's write the H3O plus first. Will produce the phenoxide anion. Now the phenoxide anion is resonance stabilized. The lone pair can dump in here. And you can move the lone pair around the ring. Such delocalization of the negative charge around the ring does make phenol more acidic than regular alcohols. And you have quite a few resonance contributors. I mean, if you look at the structure, resonance structures I've drawn, you see there are 5 resonance contributors that effectively suggest quite extensive delocalization. Now compare these two such scenarios to that of what happens when you have a carboxylic acid. If a carboxylic acid reacts with water, we get H3O plus plus CH3, C double bond O, O minus. And I can draw a resonance structure with CH3 sub C double bond O minus, where I move the pi electrons out on the other oxygen. And at first glance, if you look at this, you see that you get only 2 resonance contributors. And at first glance, you might say, oh, the phenol produces more resonance contributors, delocalizes the negative charge more, hence it's more stabilized, so phenol should be more acidic. But in actual fact, if you look closely, you see this is not the case. If I label the structures in phenol, the anion A, B, C, D, E. In structures A and E, the negative charge is localized on oxygen. The structures that move the negative charge around are B, C, and D. However, B, C, and D are minor contributors because they disrupt aromaticity. The aromatic ring is lost. As a result of their minor contribution, the phenoxide anion is less resonance stabilized than the carboxylate anion. Even though you only have 2 structures, these structures are equivalent and equal, and the negative charge is distributed between 2 oxygens. This simple resonance between 2 structures leads to more effective delocalization of the negative charge than what you see in the case of the phenoxide anion. Okay. Based on these trends, we can now attempt to rank acids and rationalize them in terms of their relative strength, specifically carboxylic acids. We can incorporate the concepts of both resonance and, not only resonance, but we can incorporate inductive effects, atomic size, electronegativity, etc. Okay, let's attempt to do that. Indicate which is the stronger carboxylic acid. And why? The molecule carbonic acid or the molecule acetic acid. Well, if I react these both with water, as follows. React these both with water, I'll produce H3O+. And carbonic acid will deprotonate, producing bicarbonate. Acetic acid will deprotonate, producing acetate anion. Now, you must remember to incorporate all your ideas that we have just covered. I'll give you an example. If I was being simplistic, I might say, oh, methyl, carbon is inductively donating electrons, destabilizing the anion. Oxygen is electronegative, withdrawing electrons, the HO group, and so it will stabilize. And therefore the strongest acid would be carbonic acid because the electronegative HO group stabilizes the CO2 minus. And on the surface that appears sound. But you must look carefully, you must consider every factor. If I look at CH3, CO2 minus, yes, the negative charge can be delocalized. I can draw this resonance contributor. And in both cases, methyl is inductively electron donating, destabilizing the anion somewhat. Now compare this to the resonance structures I can draw for the bicarbonate anion. Well, indeed, nothing's changed. I've got a minus. I can delocalize that minus to the other oxygen. But I can do something else. I can also dump in this lone pair and move those pi electrons out. If I do that, I get this. Look closely at this resonance contributor. What have I done? I have donated electrons, pushed electrons out into carboxylate by resonance. Resonance effects are usually stronger than inductive effects. And because of resonance donation, I've put a negative charge out onto the oxygens. Even though this is a minor contributor, it's pushed in more electrons than we'd probably get from the inductive donation of the methyl. What that means is this resonance contributor is destabilizing the anion because it puts adjacent negative charges on both oxygens. Now remember, this is working against electronegativity effects, where the oxygen withdraws by electronegativity. However, when we compare resonance effects to electronegativity effects, resonance effects usually win out. So although the oxygen withdraws electrons by electronegativity. It donates electrons by resonance. This resonance donation probably pushes more electrons into the carboxylate than the inductive donation of the methyl. The net result of this is it destabilizes the anion, making it less likely to lose a proton, meaning the carbonic acid is not the stronger acid. So you have to remember to look at all aspects of the trends and try to combine them when you're looking at trying to rank groups in trends of acidity. Now, one of the things we're going to want to rationalize, one of the trends we're going to want to rationalize, are the trends of acidity for benzoic acid. And so what we're going to do is we're going to look at some substituted benzoic acids, their pKa values, and we're going to try, if we can, to rationalize them or explain them. And what we're going to do now is we're going to draw benzoic acid. Benzoic acid has a pKa value of approximately 4.2. And we're now going to make 3 columns where we have ortho substituted benzoic acid. So we're going to put some substituent in the ortho position. We're going to compare that to meta-substituted benzoic acid. Some substituent meta to the benzoic acid. And then we're going to put some substituent in the para position. Okay, now, so we're going to compare ortho-substituted benzoic acids to meta and to para. Okay, and we're going to start with different R groups. These will be my R groups going down, and the first one we're going to look at is methyl. What if the R group is methyl? If the methyl is ortho, we have a pKa of 3.9. When it's meta, we have a pKa of 4.3. And when it's para, we have a pKa of 4.4. The interesting observation that we need to explain here is why is the ortho more acidic than benzoic acid, while the meta and para are less acidic. Now remember, methyl groups are inductively donating. They push electrons into the ring. And because of that, we would think that pushing electrons into the aromatic ring would cause the aromatic ring to push electrons into CO2-. We would expect the methyl to be less acidic. And while that occurs for meta and para, it doesn't seem to really make too sense that the ortho should be more acidic. Well, perhaps this is a glitch. Let's look at some other groups. What if we have HO, a hydroxy group? Hydroxy groups, as we saw in our previous example, are electron withdrawing, but sometimes they can donate electrons by resonance. Because of that, it might push electrons to be less acidic. But again, ortho is more acidic. Instead of 3.9, it's quite a bit more acidic, pKa around 3.0. Meta is slightly more acidic, 4.1, but para is less acidic. Methoxy, again the ortho is more acidic. The meta is more acidic. And the para is less acidic. Interesting. If we now compare bromo groups, again the ortho is quite a bit more acidic. Meta is quite a bit more acidic, but para, although it's still more acidic, is less so. Again, we could go with chloro, 2.9, 3.8, 4.0. So chloro parallels bromo. And of course, put the very electronegative nitro group, and we drop from 2.9 down to 2.2. That's a 9. 3.5, more acidic right across the board, and 3.4. So if we take a look at these trends, and they are given to you in your notes, so you can keep looking at them after I erase these and we start looking at them individually, we can start asking what is going on here. See if we can explain the trends. Let's start by looking at the bromo and chloro cases. In the bromo and chloro cases, the pK values of 2.9, 3.8, and 4.0 for ortho, meta, and para reflect what's expected for electron withdrawing groups. The electron withdrawing bromine and chlorine is closest when it's ortho to the carboxylic acid. So the CO2H loses a proton, becomes a CO2-. The electronegative effect would withdraw electrons from the CO2-, stabilizing its formation when it's closer. As it moves further away, the effect would drop off. It would still be there, but it would be reduced. That's exactly what we see for the bromine, bromo, and chloro. The bromo and chloro, we get 2.9, then 3.8, and 4.0. Nitro is a little more complicated. We get much stronger effects when we're ortho, but meta is closer than para, and yet it's slightly less acidic. That requires explanation. How can we explain that? Well, one of the things we can do is examine what happens when we have nitro groups, ortho or para, and compare that to meta. So I'm going to take the two anomalous situations, the para and meta, compare them. And let's start with the para. Now in the para case, I'm going to work on the CO2-. And I'm going to just put CO2- here. Remember, NO2 looks like this. And I'll draw this structure when I need it. Right now, there's a negative charge on this oxygen, positive charge on nitrogen. Now, with an NO2 group, you can actually draw resonance structures in which you move the pi electrons out towards the nitrogen and away. These are minor contributors because you're increasing charge separation, but they're real. They may be minor. The net result is you put a positive charge here. We now have a double bond N. We have an O-, and now an O- here. Minus, minus, plus on nitrogen. And we have a CO2-. Now draw the next contributor. I'm going to move these pi electrons towards the positive charge. That'll put that there. Put a plus here. And the CO2 minus. And we can keep drawing our double bond here. Minus, minus, plus on nitrogen. And of course we can do that one more time. Which is going to be this, plus CO2 minus. Now while you draw these structures, make sure you keep that table handy of those pKa values so you can compare them. And of course the last thing is move the pi electrons back and get back to an NO2. I'm going to just put NO2 now. Okay, so I was able to draw 5 resonance contributors which move a positive charge around the ring. Now let's do the same thing for when the group is meta. Drawing a lot of resonance structures here. Now we have the group here. Okay. Well, I can move these pi electrons out. If I do that, I get this. If we do that and move that, we'll end up with a plus in this position. And of course I can move these pi electrons if I do that. Move these 2 electrons here. Takes a little time to draw these. And finally, if I move these pi electrons back, and I dump in a lone pair, I will get back to our I'll just put NO2. Now, if you compare the resonance structures for the meta versus nitro, and I'm going to write the pKa's again. Notice that the pKa for the meta was 3.5 and the pKa for the para was 3.4. Now the para, being further away, should have less of an electronegativity effect. This smaller electronegativity effect should stabilize the CO2 minus light, which means it should have had the larger pKa. So something must be compensating for the para to allow it to undergo or behave as if it's a stronger acid. And the resonance structures reveal what this is. Notice that one of the resonance contributors puts a positive charge right next door to the CO2 minus. This positive charge will withdraw electrons and stabilize the CO2 minus. Notice, however, if you draw the same resonance structures, the plus is here, the plus is here, the plus is here, but it never ends up next door to the CO2 minus. So although the NO2 group is further away from the CO2 minus and electronegativity effects will be reduced, by resonance it can get the plus right next door and compensate for its reduced electronegativity, allowing its pKa to be reduced, making it a slightly stronger acid. Of course, the same types of structures can also be drawn for the ortho as the para. And you should take a look at your notes, and you should be able to do that. Now, we have a similar dilemma in the case of the acidity of the methoxybenzoic acid derivative. And we need to look at its contributors as well. Now, if I replace these structures and I draw them again, oops, but instead of looking at nitro groups, I'm going to now put RO groups on the ring. I'm going to have an RO in the para position. Okay. Unlike NO2, which by resonance withdraws electrons, RO groups can pump electrons into the ring by resonance. The oxygen's electronegative, yes, but by resonance the lone pairs can be dumped into the ring. The net result of this, of course, is a negative charge that occurs here and a double bond OR+. So there's a lone pair there, and we get a positive here. If we continue with this right around the ring, we will pi bond, double bond, OR, lone pair here, minus, CO2 minus. I can dump these here, and these can move out here. And lastly, it takes patience to draw these structures. If I dump this here, move these pi electrons back out on the oxygen, get pi bond here, CO2 minus, and back to my OR. Compare this situation with what happens when OR is meta. The meta OR can dump in lone pairs, to make a double bond to the oxygen and move a negative charge around the ring. We have a lone pair here. This lone pair can dump electrons here. Now we can dump this in here, move this over here. And what we have then is we can dump the lone pair here, move pi electrons out, and get us back to the closed aromatic ring with an OR group. There we go. Now compare these sets of resonance contributors. Specifically, focus in on this resonance structure right here. Notice that in this resonance contributor, a negative charge ends up beside the CO2 minus. Two negatives beside each other are repulsive. This destabilizes the anion, making the para less acidic. And indeed, compared to benzoic acid pKa 4.2, para has a pK of 4.5. Well, why would the meta have a pKa of 4.1? The same resonance structures never put the negative charge adjacent to the CO2 minus. Negative charge moves around. But the oxygen is still also functioning as an electronegative group. So the negative charge moves around the ring, but never ends up adjacent to CO2 minus. The electronegative oxygen, on the other hand, the electronegativity of the oxygen, helps stabilize the CO2 minus somewhat. And so its pK is very close to that of benzoic acid. It's just a little more acidic. Of course, if this rationalization works, we have one major problem. Look at the pKa of the ortho. If I had ortho, I could draw the same resonance structures as I got for the para. In fact, these are drawn in your notes. Wouldn't you get this repulsive situation with the ortho? Wouldn't that make the ortho have a larger pKa? And in actual fact, the ortho has a pKa of 4.1, making it more acidic. And what about when we have hydrogen in place of the R group? This is when R is alkyl. So red is R alkyl. What is it? What are the pKa's when we have a hydrogen? Well, when we have hydrogen, the pKa for the para is the same. Well, that makes sense because whether this R is carbon or this R is OH, we'd get the same resonance structures. pKa for the meta is the same, 4.1. Again, same resonance structures. Here, electronegativity plays the big effect and makes it slightly more acidic. Whereas up here, because resonance gives you adjacent negatives, it's repulsive, it's a little less acidic. What about the ortho? Well, like the methoxy, or when R groups, or carbon for R groups, you get more acidity, and that's at odds with our resonance structures. When it's an H, it's even more pronounced. It's a 3.0, a big jump in acidity. How do you explain that? Well, certainly this requires some special explanation. So far, we've seen large jumps in acidity for every group that has occurred in the ortho position. In other words, it didn't matter whether it's electron donating, like a methyl, or electron withdrawing, like nitro. There has been a fairly large increase in acidity when a group is ortho. Why would that be the case? The answer to that lies somewhat in steric effects. That is, when there's a bulky group here, no matter what it is, there is a favored loss of the H due to steric effects. This loss is referred to, this preference for loss of the H, called the Ortho Effect. The Ortho Effect can be summarized as any effect, electronic or steric, which increases acidity because of the occupancy of substituents in the ortho position. It's often attributed to steric repulsions between ortho substituents and the carboxylic acid groups, leading to the loss of a proton. In fact, this is somewhat pronounced when you have a methyl. See, methyl is inductively electron donating. It should destabilize, right? It should push electrons into the room and destabilize the formation of CO2-. Now, this inductive electron donation should fall off the further away you get, but all of the methyl substituted benzoic acid should be less acidic than benzoic acid. Now, this trend holds true for para and meta, right? But when you have ortho, the pKa goes to 3.9. Clearly, there's another factor. And this factor is attributed to steric effect, the methyl group's proximity to CO2- favoring the repulsive loss of the H+. So you need to remember the ortho effect. Of course, one last question needs to be announced or compared. Why is there such a huge difference between OCH3 and OH when it's ortho? Why is OCH3 a pK of 4.1 and you go to OH and you get a big jump? Well, OCH3 has the ortho effect, so would an OH group, but the OH group has something else. Can you see what that something else would be? If you said hydrogen bonding, which stabilizes the negative charge, you'd be right. There's hydrogen bonding there. And so this extra hydrogen bonding gives you a whole drop of 1.1 in the pKa value. So in the case of the ortho group, you have the ortho effect plus hydrogen bonding. So all of the trends in that original table for different substituted benzoic acids, all of those trends in pKa values can be rationalized in inductive effects involving electronegativity or electron donation, as well as resonance effects in the aromatic rings. All right. Well, that seems to be a good place to stop. Focusing on the acidity of carboxylic acids is one of the most fundamental aspects of its reactivity. And so hopefully this has been useful. I'm Dr. Brian Lloyd, and this is my Scribblecast.